All right, let's talk ZettaCache. So, as you heard this morning about a little bit about ZettaCache, but most about the Zetta object store, I want to start actually by sort of reviewing a little bit about the object store, sort of set context here. As you heard this morning, we use cloud as a backend and have sort of infinite capacity because of that, but we trade that for high latency. Now, this works really well for large block streaming workloads, but as we saw this morning, conventional wisdom says that's not a good model for highly transactional latency workloads, such as what we want it for, and mostly because of latency. But we know how to deal with latency in ZFS, right? You can mask your asynchronous write latency with a slog. You can add a cache to mask your read latency like the L2 arc, and you should be good to go, except for those troublesome workloads. And that happens to be the Delphix use case. We have a small block size, average of 3K, means that a high proportion of metadata to data. We're talking about random IO workload. That means little IO consolidation or streaming. We're talking large working sets. So, for example, a 50 terabyte working set, which would mean upwards of 18 billion blocks that we need to keep track of, and want to operate in a constrained memory size. Right, something on the order of 128 gigabytes. That means we can't keep all that metadata in memory. So the L2 arc is simply not going to do the job for us, right? It can't support the target working set, at least not in 128 gigabytes of memory. Those 18 billion blocks, on average, you're going to see almost 100 bytes of metadata per block in the cache. Means you're going to need on the order of almost 2 terabytes of memory just to manage the blocks in the cache. In addition to that, it has a FIFO eviction policy, which can be and is very ineffective when trying to size your cache. So even if you get a lot of data into the cache, you can't depend on unused data not clogging things up, right? It doesn't get evicted effectively. And in fact, you can have frequently used data that's in your cache that can get evicted and will be evicted eventually, just as it works its way through the FIFO queue. So you really can't size the cache to guarantee that you're going to get your working set to stay there. So we want something a little different. Our goal here is to get performance comparable to ZFS on EBS. And that means ZFS backed with S3 with a ZettaCache based on EBS storage. And we want to reduce that 20 millisecond latency to 2 millisecond latency. So the high latency from the S3 needs to be averaged out to be a nice 2 millisecond latency, hopefully from our ZettaCache. We want to support very large caches. We want to do that with small memory footprints, so on the order of 2 gigabytes, less than 2 gigabytes for that 50 terabytes of cache. So that means it has to be persistent by design, not as an afterthought. And we need an improved eviction policy. Rather than FIFO, we're looking at LRU. We want to be able to understand the cache size and its effectiveness. So let's talk architecture. So this is what the object agent looks like in ZFS, right? It's as George talked about it, it's ZFS object VDEV communicates through to userland to talk to the ZFS object agent. And within that, we have the ZettaCache, which is where the ZFS will look first. The IOs will be looked for first. And if not found there, it goes off to look in the cloud. Why did we put the ZettaCache up with in the userland as opposed to embedding it in the kernel as our other caches are? A few good reasons. One, this architecture, we want to keep ZettaCache very close to the Zetta object agent. for efficiency's sake, right? It's the primary consumer of this, and it made sense then logically to put it up there. It keeps us separate from the bulk of ZFS, so we could develop without having to inject a lot of new code path or changes into the ZFS IO pipeline or other parts of ZFS architecture. This is a separate entity completely. So it really gives us an easier environment to do our development because it's in user land. We are not dealing with a new kernel every time we make a modification. We are also able to develop in Rust, which is really nice. So it's helped us do our development cycle to be much improved. We can cycle things very quickly. I think I talked about these points, but one of the questions you should probably have in your mind right now is it going to perform? If it's in user space, can you perform? And the answer is, for us, at least right now, absolutely. Our needs really are only to be able to drive an AWS instance efficiently. Sorry. And most AWS instances do less than 20K apps to an EBS storage. And so we can do that now easily using a simple pre-read, pre-write interface. So it certainly meets our needs, and we believe that it will meet our any needs in the future because it's possible to go in user space as almost fast as kernel using userland NVMe drivers, for example, or the IOU ring interface. So we don't believe this is going to be a bottleneck to our performance here. All right, design. Basic components of the ZettaCache are an index used to find data in the cache, some form of allocator to store data in the cache, and a checkpoint mechanism to create recoverable state. Now, if you're looking at this picture on the right, you might be thinking to yourself, you know, that looks an awful lot like a diagram of a file system. And file systems are hard. And if you're thinking that, you're right. That's true. Both those things are true. It does look a lot like a file system, and file systems are definitely hard. I know. As part of the team, we spent 50 engineer years before ZFS went to first customer ship. So it was a big effort. So we need to simplify our requirements. We aren't actually going to develop a new ZFS here. We're developing a cache. So we should step back and say, all right, what are the actual requirements we have for this storage? And that is a persistent searchable index that doesn't need to be, it can't in fact be fully cached in memory, but that can support lookups in at most one read, right? Remember our goal here is to be able to satisfy or to emulate ZFS on direct storage. We need a block allocator that has a small memory footprint as well and is resistant to performance impacts from fragmentation. And we need some sort of way to transition from state to state so we can atomically update our on-disk state and maintain consistency. We use checkpoints for that. So let's look at some simplifications. One, we're only going to have one block pointer for each block, right? We don't need any snapshots or other, most of our metadata needs are pretty simple here. And in fact, we can store all our metadata in logs, right? There's no logical overwrites of data. We only have to do logical appends. And our logs are stored as lists of extents of large allocations so that we don't have a lot of blocks involved in our logs. Large log blocks where we simply add log elements to it, and we need to track sort of where the end of our last element is within the extent, and there's no need for a lot of indirect block structures to manage that information. So we're really developing a new from scratch simplified block storage here. And we also have a very simple interface, right? Our operational flow is lookups. Look up something in a cache, so you can look it up, query the index. If you find that entry in the index, then you're going to read that block from the cache. Or insert a new block where you're going to look it up query the block, get from the block allocator a new space on disk for that block, and that block allocator will then insert a new entry in the index to say, here's that new block on disk. So I want to talk about the specific elements there, the index and the block allocator, because those are the most interesting pieces of the current design. I skip one, sorry. So the index is just a way to map a block ID to a disk location. And if you think about ZFS today, for example, in the ARC, we have a large hash table that does that for both ARC and L2 ARC. But that's a little bit of a complicated data structure to manage persistently, to have a persistent representation of. So we've chosen a simpler data structure to represent it, which is essentially a log structured merge array, which is a mutable ordered array or run of entries that we store persistently, and then we track pending changes in logs in memory, right? So whenever we want to transition from one index to the next, we apply our set of pending changes to the old run to produce a new run. So the old run is ordered by index ID, and we apply our pending changes to produce a new run on disk. In addition to that, oops, sorry, we skipped 2. So how does that look on disk? What does that run look like on disk? The run on disk is actually an array of chunks, where the chunk is sort of our logical I/O unit, and it's a large list of an array of entries, where each entry is that mapping of a block ID to a disk location. And then in order to be able to achieve our ability to read from this or look up an item in this with only a single read, we also keep stored a summary of the mappings, array of mappings, which map the first block ID in each chunk to its location, to the chunk location on disk. So that, and then we keep that mapping in memory. So that's our first lookup point. So when we want to look up a block in the index, we consult our in-core summary. We find it from which chunk that block ID would be in if it existed in the cache. Then we can read that chunk and look in the chunk to see whether or not we actually have an entry for that particular block ID. All right. Now, pending changes are kept in memory in a pending changes tree. That's for efficient lookup and inserts. But we also need to keep that persistent. All right, we don't need that persistent because we don't want to lose pending changes when we panic or exit from the log. So we need to maintain a persistent version of that, which we call the operation log on disk. So whenever we adding entries in the pending changes tree, we add entries to the end of our log. This is a simple list of entries on disk, append only, and we can, this is allocated in large chunks, large extents on disk, and we are simply adding new entries as we add them to the pending changes tree. So to move from state to state, we simply create a checkpoint about every minute where we persist the pending changes. That means we make sure all our entries in the pending changes tree have been written out to the operation log. And then we store in that checkpoint a pointer to, or basically the metadata necessary to find that pending changes list, as well as a pointer to the index, which is already persistent on disk. So if we do have a crash, we lose less than a minute of cache data in the crash. This also represents sort of a unit, a point of consistency within the cache. So each checkpoint is a consistency point for the cache itself. So how does that work? Well, if we have to, when we reopen the cache from any point at any point, we first read the super block in a well-known location, which points to what the current checkpoint is, the current checkpoint block. We read that checkpoint block. A checkpoint block has essentially our metadata. Within it, it has a pointer to the index and summary, index run and summary, as well as the operation logs. These are all the components that make up our index. So what's going to happen is it's going to simply read in the summary into memory and ingest the operation log and replay it to reconstruct the pending changes tree. Once that's completed, we're now able to operate the caches normally. But we can't accumulate these pending changes forever, right? Pending changes represent a set of deltas to the index. And if we just continue to change and accumulate entries in there, it's going to get too large over time. So we need to merge those pending changes periodically into the current run to produce a new run, as I illustrated in an earlier slide. We trigger these periodically when we sort of accumulated on the order of tens of thousands of pending changes. And we run this as a low overhead IO task in the background, so it doesn't interfere with normal cache activity. So we read the old index in order. We apply the pending changes to it. When we come across, for example, an insert, we insert a new entry from the pending changes into the index, so the index grows. If we find a remove request, we remove that entry. Or if we have an access to a block, then we update the A time. I'll talk more about A times a little bit and how they're used. But the index also itself cannot grow forever. If the index grew forever, obviously the index is a mapping of where all the blocks are in the cache, and the cache is finite in size. So eventually you're going to have an index that represents a full cache, and we'll need to start evicting data from the cache so we continue to grow and absorb new entries into the cache. So we need to evict periodically. As I mentioned earlier, we'd like to evict based off an LRU algorithm. So this is where we use our A times, our access times. Every block has a last access time. This is incremented every 10 seconds. So the access time is really a measure of sort of artificial time from when the cache was first created. Every 10 seconds it increments, and every block that is inserted into the cache or read from the cache during that 10-second period is marked with that particular access time. This gives us sort of an approximation of an LRU if we create this histogram that you see on the right. Every time we ingest a block, we add the size of the block to a histogram at that A time. So on the diagram on the right, the numbers in this diagram represent gigabytes of data. So for example, at A time 1, we ingested 20 gigabytes of data. At A time 2, we ingested 30 gigabytes of data, and so forth. If we access a block, for example, we are, let's say, at A time 7, and we access a block at A time 2, then that read causes us to change the A time of that block. And so we would, and say it was a 8K block, we would decrement our slot 2 of the histogram bucket 2 by 8K and increment slot bucket 7 by 8K, and that's how this particular histogram grows and shrinks and changes over time. Now, when we want to evict, all we need to do is look at this histogram and count up the space of the amount of data of space used by the blocks with particular A times. In particular, we look at the current A time in this diagram, it's A time 9, count back until we have the size of the cache size that we want to try to maintain. In our example, we're trying to maintain, say, 300 gigabytes of data within our cache. So everything before A time 5 is now evictable data. That's the old data. It's A time of all those blocks are older than we want to keep around any longer. So we can evict based off of that. So that cutoff, that A time 5 represents our sort of a cutoff for eviction, which we will now leverage during merge. So remember, merge was already going through all of the blocks, all of the index blocks, and all of the changelog blocks, pending changes blocks, to create a new index. And so it can also examine the A times while it's doing that job. And so it can, if it sees a block that it occurs, has an A time before our cutoff, that's an evictable block, and it becomes evicted. So you can see in this example here, we have a set of pending changes, we have an old run, and we're generating a new run, and we see that we have blocks at 4, 5, and 9 that are all have an A time of before 5. And so when we write our new run, we're going to come along and say, all right, 4, that's evictable, 5, evict, 8, 9. Well, we don't actually evict 9 because we also have a pending change for 9, which has a newer A time. So that takes priority. It says, all right, we actually have modified 9 since our eviction cutoff, and so 9 goes into the new index. So now what's really kind of cool that now that we have this sort of mechanism for evicting blocks or for managing blocks based off of A times, this A time histogram, is we can actually leverage that same histogram to answer the age-old question of how do you want to size your cache? How effective is my cache at a particular size? So we use that same eviction, same A time histogram to generate a new histogram, which we call the size versus hits histogram. So size versus hits histogram leverages that eviction model. And so whenever we get a hit in the cache, we can say, all right, this block we just hit in the cache, what was its A time? Its last A time, not the current. It's about to get updated, of course, because we just did a hit. But what was the hit, the A time when we actually found it in the cache? That tells us essentially the A time at which it exists, the latest A time it could exist in the cache. And now we could count up all the space that was before that A time, and includes that A time, and say, all right, that would be the minimum cache size we would need in order to guarantee that we would have hit on that block at this time. So that happens for every single hit in the block. We maintain this new size versus hits histogram, and using this, leveraging this information, we can generate a report that looks like this. So on the right, you see output from our ZettaCache report hits command. And this represents a little bit of a toy example. It's a small working set, but we're getting about 98% hit rate in this cache. But 97, look at the data on the right, you see that 97% of those hits are occurring within the first 3 gig of the cache, according to that graph on the right. So we could take a look at this and say, hey, you know, if I was to have the size of this cache, I could still retain and maintain a 97% hit rate. That's pretty cool. So it could actually tell you that I am, based off this particular workload, I have more cache than I need. I could get by with less cache. Now we could also now extend this idea and say, all right, not just maintain this information for the current cache, but if we extend our A time histogram data, we don't throw away sort of the historical data that's contained within it, because we have, remember, we have the A time histogram data records it for all of our A times. We can choose when, if ever, to evict information out of that log, that data. We can use that history of size to actually say, well, you know, I looked up this block. Now, we also have to keep a little bit extra data in our index, of course, which are the ghost entries for blocks which we've evicted recently. But let's say we keep another cache size worth of data around that way. Now, when I look up that block, I can say, all right, the index, I looked up that index, that block in the index, and it said, no, I don't have that block, but I used to have that block. And when I had it, it was marked with this A time. So from our previous example, say it was A time 3, and I evicted at A time, everything before A time 5. Now I can count up all the data in the A time histogram and say, all right, well, the cache would have been this big at this A time. And using that, I can predict then, all right, if I had a cache that's a little bit larger, I could have kept this in memory, and you would have had a hit. And that could generate a graph with something like this on the right, where we see that, yeah, the first same cache size, same 7 gig cache, but now we have a larger working set, and we're only getting about a 68% hit rate in our current cache. But if we project it out into our ghost cache, we see that around 10 to 11 gig, we're getting up to 97, 98% hits. So this tells us that, all right, I could potentially get better hits. I get potentially up to 98% hit rates if I was to double the size of my cache. And that can be very valuable. Again, all this depends on being able to run this data for a period over which you're actually operating sort of with normal working sets to understand how your hits are going to work within your cache. All right, at this point, I want to change gears a little bit, and I'm going to turn things over to Serapheim to talk about the block allocator. Serapheim.
So first of all, what does a block allocator do, right? The block allocator is a subsystem that determines where data should be placed on disk. And when designing one, there are like multiple things that we should be taking into consideration. Things like runtime performance. How quickly can we satisfy allocation requests? Storage utilization, basically making sure that we are making the most out of our hardware and minimizing any wasted disk space. Other factors like contiguity of allocations, where some devices like hard drives get a big performance boost whenever we try and allocate blocks contiguously on disk. And finally, the memory consumption of the block allocator's metadata. Basically, the block allocator needs some kind of in-memory structure to keep a track of what is allocated and free on disk, right? So we want to make sure that these structures don't take up too much memory and we play well with the rest of the system. So before I go ahead and go over what we ended up doing, I'd like to do a small recap and look at what ZFS already has in terms of block allocation. So the block allocator in ZFS is part of the storage pool allocator, or what we call the SPA. And what the SPA does is basically dividing each VDEV into 16 gigabyte regions we call meta slabs, from which we allocate and free blocks of arbitrary sizes. Now, these meta slabs are represented in memory with something we call range trees, and you can think of a range tree as a standard tree data structure where each tree node, basically represents a free region on disk. Now, these range trees can get pretty big, especially for big pools, but even for smaller pools, depending on your workload or the history of the pool. So for that reason, we only keep a subset of all these range trees, MetaSlab range trees loaded at a time on our system. Specifically, we only keep loaded the ones that we are allocating from, so we can find where the free space is on disk. But as I said, we only keep a subset of them loaded because we want to conserve memory. So this is more or less the scheme that the design that we have currently today, and it has served us well, and it continues to serve us well. But it doesn't mean that it doesn't come with its own flaws. Specifically, within Delphi, what we've seen is on our database workloads, which are mainly characterized by small and compressed random writes, we see that our pools over time having free space scattered all across their meta slabs. And because these writes are compressed, fragmentation is pretty high because we allocate all kinds of block sizes. And when capacity gets at pretty high percentages, it's just hard to find space. So distilling these kind of like samples into like actual problems, what ends up happening is that we're spending a lot of CPU runtime and a lot of disk IOs just constantly loading and unloading MetaSlab range trees. And the memory overhead is high because these range trees can get pretty big. And again, reiterating on the high capacity part, where allocations can start failing and gang blocks may kick in, which make fragmentation even worse and kind of create this vicious cycle. That's not to say that because of this, the SPA design is not good. It actually satisfies the requirements of a file system like ZFS pretty well. But for the ZettaCache, we're designing a cache which is different from a file system. So we went back and kind of reconsidered some of these trade-offs. Specifically, things like the contiguity of allocations, right? This is something important for hard drives, and file systems need to support hard drives. But now we're talking about the cache, like the ZettaCache, where we most probably going to be using something like SSDs or NVMe devices. So contiguity of allocation of this kind of device is not as important, and therefore it doesn't need to be a major factor in our design. Second part is the disk space utilization, right? We were talking about the SPA, the file system. We strive to make the most out of our hardware. Our goal is, 100% utilization. But for something like a cache, yes, disk space utilization is important, but it's not the main factor in the design. Everything is the hit rate, right? As long as your hit rate is high, as long as your hit rate is good, it means that your cache is working, it does its job. And finally, memory consumption. ZFS is a file system, and basically what the SPA tries to do is manage unlimited storage with limited RAM. Basically, so you can keep adding more storage to your systems without having to think about the RAM that you're actually using. And this is the whole reason why we do the whole dance with loading and unloading MetaSlabs. Now, for a cache, this is still a very important concern. This is part of the design because it's a valid concern. But our goal is not as strict. We can be more flexible because we're talking about a cache, right? Unlike a file system, you can actually blow up the cache, not lose any data, take a temporary hit in latency, and potentially reconstruct your cache in a manner that's more efficient for your system. So here's what we, after reconsidering all of these trade-offs, here's what we ended up doing. Basically, block allocation on the ZettaCache works like this. We take the cache and we divide it into 16 megabyte regions we call slabs. And there are three types of slabs. There are the bitmap-based slabs, which are kind of like modeled after a true slab design, where all blocks are of the same size. And I have on the bottom left an example image of a bitmap-based slab, I say 5K blocks, where you can see like each slot is of equal size, regardless of its whether it's allocated or free. And then we have the extent-based type, where it kind of resembles meta slabs, and it's mostly used for block sizes that are bigger, but they basically contain variable sized blocks. And you can see on the bottom on the center, there's an extent-based slab picture with a 20K block that's allocated, a 50K block, some free space, and a 31K block. And finally, the last type is the empty slab type. This is the completely unallocated slabs that can be converted on any of the other types on demand as we see fit. Now, I'd like to talk a little bit more about that. Basically, how do we decide what kind of slab types do we want and need? And what exactly is our allocation scheme on top of these structures? So what we do is we group our slabs by block size into what we call a slab group. Now, for any incoming allocations that are less than 16K, we have the slab groups that are backed by bitmap-based slabs, basically the bitmap-based slab groups. And we have a group for every multiple of 512. 512 bytes, 1K, 1.5K, 2K, all the way up to 16K, where basically when I say it, the 2K slab group, I mean the group of slabs that are bitmap-based that support 2K allocations. And then for more than 16K allocations, we have two extended base slab groups, one group for less than 64K and one group for more than 64K allocations. Now, this distribution of like block sizes into groups, it's not set to stone, it's actually tunable. But regardless of that, each slab itself may change its type and migrate between groups during the lifetime of the cache. So just to give an example, it really depends on the workload. So let's say you just created your pool, you have your data, and you put your cache in action, and the cache in the beginning is empty. You start reading, let's say, a data set that has a lot of 3K blocks, and we start caching those blocks in the ZettaCache. So we go to the block allocator and we keep requesting blocks of 3K. So what the block allocator will do is convert all its empty slabs to 3K bitmap-based slabs, put them into the 3K group, and start allocating and using the space in those. And then later, if for some reason your workload changes to 6K blocks, what the cache will do is basically gonna start caching those and evicting the old 3K blocks, basically slowly freeing over time all these 3K slabs that it made, converting them to empty slabs, then converting them to 6K slabs to satisfy the 6K block allocation. Now, this was more of an example to just kind of like describe what the runtime of this scheme would look like. Most of the time in the real world, the things are not as black and white. Basically, you won't just have 3K incoming blocks or 6K, but most probably you're going to have like all kinds of block size being requested by the block allocator, effectively distributing all these slabs into all these different slab groups. And another thing that I simplified a little bit was that you won't as often see slabs getting completely freed up. Most probably you will see something that looks like the first row on this image here, where we basically have some slab groups that are like pretty full and other ones that are not as full. And in this specific case, I'm highlighting this kind of like new perspective that we have now on fragmentation. Basically, before with the meta slabs, we had this block level fragmentation where because meta slabs had variable length block sizes, we will have fragmentation at the block level. But now we've kind of like traded off that problem from fragmentation at the slab level, where we can have underutilized slab groups leading to stranded space. In this example, the first row, we see that the 3K slab group, has a lot of slabs, but it's not actually using the space within them that efficiently. And that's a problem, right? But for our cache, our block pointer kind of like scheme is a lot simpler, right? Unlike the SPA and ZFS, where we have this kind of like complicated graph structure of block pointers in direct blocks that's impractical to move around. Our blocks are fully indexed, meaning we have exactly one pointer for each block. And that can make it easy for us to defragment our data and free up slabs. And basically, when I say defragment, I mean literally locate the underutilized slabs, let's say these 4 slabs in this example, move their data around. In our case, we just moved them in this first slab right here, and we ended up freeing them to be used for another slab group, potentially the 5K or the 6K one, because these look almost full. So that's kind of like an overview, a high-level overview of our design, and that's more or less what I wanted to cover today for the sake of time. I just want to spend one last minute comparing our new design for the cache to like what would have been if we were actually using the SPA allocator for the cache. And with our new design, we get greatly reduced CPU and disk IO activity because we don't spend time loading and unloading the block allocator's metadata, specifically the meta slab range trees, right? And in turn, our performance is not affected at high capacity or even high fragmentation. Moreover, our memory overhead is greatly reduced because on average, we'll be using bitmap-based slabs and effectively representing a block on disk with only 1 bit in memory, right? Versus the 8 to 12 bytes that we are currently using today per range tree segment for the meta slab range trees. And finally, I just wanted to highlight that overall our design is a lot simpler, right? We have our requirements for a cache that are in comparison a lot less than the list of requirements that you need to implement a file system. So it's not that we had this genius idea, it's more like we looked at our requirements and we came up with a simpler design. And reasoning about its performance is a lot more straightforward, and we hope that it's going to be easier to debug in production too. That's all I wanted to cover today. Mark, would you like to?
All right. So that's pretty much is it for the bulk of our material that we had to present. But I would like to leave you with a couple of thoughts. One is, could you modify ZettaCache to work with traditional block-based storage? And I talked about our architecture and the fact that we had chosen to implement ZettaCache in user space to be tightly integrated with the object agent. But I think, and I believe it is still possible that you could leverage ZettaCache from in a sort of typical block-based storage configuration by injecting the cache check into the IO pipeline, so that at some point, once you're past the ARC and L2 ARC checks in the pipeline, and you're actually going out, starting to go out to disk, you could query even an upcall up to ZettaCache and say, is this block existence in my some sort of fast storage there, and get a response back. So I think it is possible. Perhaps a more radical and interesting thought experiment is how could you use ZettaCache as primary block storage and not just cache? And as I mentioned, and as Serapheim mentioned a few times during his part of the talk, we made a lot of simplifications, and those simplifications are dependent on the requirements of cache, which are things like, yeah, if we don't ingest that block, that's not a big deal. It's not the end of the world because we're just a cache, and you'll just get a miss and you'll go to the backend storage. Well, obviously, that's not going to be practical for primary storage. You have to ingest all blocks. So there'd be a lot of issues to work through. but it is kind of an interesting experiment to think about. And I think it's something we do think about occasionally. I think that's pretty much all we have for our slides here. Are there any questions we can answer? So I got a question from Alan, and he was asking whether or not we could apply, when I talked about the A-time histogram and hits by size histogram, whether we could move that same concept into the existing arc and do something similar there to be able to generate interesting reports and information about it. And initially I thought, yeah, that seems plausible. But then Matt pointed out that there is more complexity in the arc. The arc isn't just an LRU cache. It's a much more sophisticated balancing cache between MRU and MFU data. And so it's going to be quite a bit more tricky to be able to do predictive analysis. I mean, you could do the analysis, I think, fairly easily on either the MFU or the MRU sides of the arc, but the fact that it's constantly shifting back and forth based off workload, I think makes trying to reason about the whole thing much more complicated. So I'm not sure how easy it would actually be to try to do something like we've done for the ZettaCache there.
The other one was about like when we're doing rebalance, is it better to just evict stuff?
Sorry.
The next question was that Paul asked was about like rebalancing versus evicting.
Oh yes, and the reason we prefer to rebalance there is again back to being able to reason about the cache. If we were just, it is simpler if we just say, yeah, we have 4 blocks in this slab, so let's just chuck it because that's only 4 blocks, right? And this is a cache, we don't care. And that would be an easier way to empty that slab out and free it up, rather than finding locations for those 4 blocks that we're trying that are left in there. But it's suddenly doing something like that begins to introduce more uncertainty now about how to reason about your cache, because now you're no longer maintaining a strict LRU policy in terms of evictions. And so if you're doing a lot of this kind of work of throwing away blocks like that whenever you need space, you really don't know how your cache is behaving. It's not even FIFO, it's just kind of a random eviction pattern. And so it kind of breaks our ability to predict. So it is certainly more efficient, but it's better if we can retain those blocks that are not eviction candidates yet.
Yeah, I think it's something that we could consider. The trade-off would be, obviously you're doing less IO. So
right.
I think that we need to, we haven't yet got performance results from like, how much eviction is really needed under, even hypothetical workloads. So, once we see that, how much like rebalancing is needed under workloads and how big of a performance impact is that, maybe we'll have to reevaluate if we see that that is more impactful than we predicted.
Agreed.
Yeah, so I think Alan's basically asking Serapheim about, like, could we apply the block allocator that you designed to regular ZFS meta slabs with having strict slabs and all that stuff?
And why haven't you done so yet?
I mean, I think one of Mark covered that a little bit on potentially using the ZettaCache as like a backend for an actual pool, but like actually changing the meta slab design right now. I mean, yeah, obviously we could try and doing that, but also things are a lot trickier. I would say on the SPA right now. So I can definitely see the benefit, but trying to have it depends on a lot of things, right? Like, sure, for some workloads it would be great, but we would have the design wouldn't wouldn't be able to be the same, because like what kind of, like, would you have like slabs within the meta slab? Like what?
Yeah, I think that even if you let's say that you work through those problems of like fitting the thing A into thing B and the complexity of modifying the current code, that's all theoretically doable. I think that one of the big challenges would be rebalancing,
Yeah.
right? Because with the cache, we can avoid most allocation failures by doing rebalancing before they occur. And then, you know, if we really didn't want to avoid allocation failures, you could like bump things up to bigger sizes. So like I do a 3K allocation, but there's no free slabs, and the 3K slab group is full. Well, try doing a 4K allocation. Try doing a 5K allocation.
Right. Or go to extents. Yeah.
You know, like you could do that, and it might give you like some kind of weird results in terms of space usage, but that seems doable. The problem is that, and you can go the other way using gang blocks, you know, which the kernel, you know, already knows how to do. But the problem is, I think the problem would be that you might be able to get into a case where that is common rather than rare, where like you might commonly have to be ganging, or you might commonly have to be bumping up to an allocation that's a much larger size. And to get out of that, you'd have to do rebalancing, but rebalancing is like extremely non-trivial with ZFS. That's like the BP rewrite problem.
If we had BP rewrite, we could do that.
But the rebalancing is almost trivial because with ZettaCache, because we're already rewriting the whole index every once in a while.
Right.
So it's just like, like while you're writing the index, you just like look up and see like, oh, what should I be remapping this? Oh yeah, okay, great. Like I'll store that new location in the new index.
Exactly.